So not only are you here in the room with us, but we are also streaming this to anyone who wants to log in on a WebEx live. So you will be videotaped, if you will, maybe just the backs of your heads, what have you, but we are recording here, and we hope to continue this at every section meeting, actually inviting other sections around the country to join, but this, as our trial, is all provided here by the folks at Cisco. So welcome. So without further ado, Fred, are you in the room? I would like to bring Fred Huffman up and have him start the presentation. Fred was one of the folks who was also a producer, and Fred will take us into the first slide set. So welcome, everyone.
Thank you, John. Good evening, ladies and gentlemen. About maybe a year and a half ago, I think it was, I started trying to socialize the idea of why not begin to start talking about networking technology. Can you hear me okay now? Better. Better? Sure. And then a couple of months ago, I got more serious about it and fired off an email, and the next thing you know, I'm mixed up in the process that we have here to do, organize and build meetings. Sometimes it's seen as not a very pretty sight, something akin to making sausage. It's kind of like, what was it they say about trapdoor encryption? It works well one way, but like sausage, it's difficult to reverse the process. And this is similar here, but I think we have a good program for you tonight. I want to try to take a few minutes and do something in the way of a scope, if you will, and attitude, a mindset for what we want to try to talk about here this evening. Basically, the kinds of subjects that come to mind when you start thinking about the kinds of change that I think we're facing have to do with what are we doing now, why should we change it, and all this stuff about an all IP facility, what are the advantages, what does it take to build a facility, and really what is it when we say video over IP. Video over IP today is a phrase that bounces off many lips, and it's a lot like multimedia was 15 years or so ago, where everybody and their brother learned around multimedia this, multimedia that, and besides the word just simply doesn't make sense, nobody really understood. There was not any common agreement or understanding on what they meant by multimedia. So I want to try to put in perspective what this video over IP stuff is, at least as we see it now, and how we see it playing into facility. I'll tell you a little bit about the speakers, and then we'll have a wrap up and hopefully time for questions before we run out of time for the evening. If you stop and take a look or think about what we're doing today, most of the existing operations are based on technical plants that were built in accordance with the serial digital interface and serial digital standards, SMPTE 259, SMPTE 292 principally. And the routers and switchers that we're using today are all based on this technology, and it's just our infrastructure that we have in place. There is a lot of Ethernet that's been around the industry for several years, but it's used mainly for so-called nonlinear transport or file transfers. You don't see much real-time content moving around over Ethernet. And all this stuff that's being talked about now so far as an all IP, live IP production facility, what are the advantages for that? Why should we mess up our nice little reliable world with something as chaotic as what the IT people seem to be able to have to go through almost every day? But what the advocates for this stuff are saying is that they believe that it's possible to leverage the scale and the cost of IT systems and products, the so-called commercial off-the-shelf hardware. And they have this nice view over the horizon about how it's going to allow improvement in workflows. So, you know, there's much to be seen about this. You start thinking about what does it take to build something like this. It's hard to not get past the fact that almost regardless if you carry it in water hoses or you put it on wire, we still are going to need cameras and servers and graphic systems and all of the same essence sources and sinks that we have today. We're going to need something in the way of what I call an IP-friendly display and waveform monitoring regimen or scheme or system. And for a long period of time to come, there'll have to be some type of a gateway or a translator or a remapper to move things from the group of bits in an SDI, across an SDI interface to something that will pass through Ethernet and Ethernet switches and IP routers. So these are the basic components that I think we really need. I want to talk a little bit about standards. And as of today, we have one that's been around for a couple of years, and we have another in the hopper, so to speak. SMPTE-NY, formerly called Transport of High Bit Rate Media Signals over IP Networks. And I'll give the first person $10 that can pronounce that acronym. I just don't, I haven't been able to figure out how, you know, you see. Figure out how to pronounce that. And I've got a $10 bill I'll give you. The other one that's in the hopper, and as I understand it in the comment resolution now is SMPTE 2059. This is going to be a whole new world for synchronizing and time code. We won't, the old way we've been doing time code for years is just going to go away. And you hear people talking about things like an epoch. How many people in the room know what an epoch is? Basically, the notion is somebody came up with this idea that you're watching time code on a display that's spinning out and going off as time goes, the sun goes up, sun goes down, time code advances and the clock advances. But if you stop and think about it, is there a way to reverse that process someplace? You know, take a Lotus spreadsheet, for example, and make that rascal count backwards down to zero. If you can reach zero time, quote unquote, in terms of timing and synchronization in a television signal, once you know when that zero is, you can turn around and calculate how to get to most any point into a program or into the future. So time code is going to be different. Synchronizing is going to be different. Basically, it's going to be I call it an adaptation and adoption of an existing standard that's been around in the test equipment world for probably 15 years or longer. IEEE 1588 V2. And that's nothing more than maybe a more precise version of network time protocol. Everybody's familiar with NTP or network time protocol? Basically, if you make that precise enough, you can use it to synchronize sync and generate time code. Now, the speakers. We've got 3 people this evening that I think are going to inform us about some of the things that we've seen and read about, heard about in the press, and heard talked about in various places. I haven't been able to shake hands with or meet Ken Morse, but a bio tells us that he is the Chief Technology Officer for Cisco Service Provider Video Technology Group. And I read enough about it to realize that this part of Cisco used to be called Scientific Atlanta. So, you stop to think about it for maybe just a couple of seconds, and somebody that was with or knows about Scientific Atlanta, I once heard it said about another fellow from Georgia, when he left one part of the broadcast business and went to a cable operation, somebody wrote him a letter and started out the letter with the sentence, "Finally, we have a friend in the enemy camp." So it seems like we have a friend here tonight from what maybe used to be the enemy camp. Ken previously served as Vice President of Client Architecture for Cisco's service provider Video Technology Group, and it says here in black and white, formerly Scientific Atlanta, driving the architecture and direction of the company's digital set-top box platforms. Prior to joining Scientific Atlanta, Ken was a co-founder and CTO of Power TV Incorporated, where he brought the first IP-based digital interactive television system to the mass market, providing a software platform and services for over 45 million digital interactive set-top boxes worldwide. Ken attended the University of Liverpool. Oh, we have a Brit. I didn't realize that. Holds a PhD in electronic engineering and a Bachelor of Engineering in electronic engineering. He's a member of the Institute of Electric and Electronic Engineers, Associating for Computer Machinery, and the Society of Cable Television Engineers. Would you please welcome Ken? Where are you, Ken?
I'm here.
The floor is all yours, man. I'll be back after a bit. We'll have a question and answer session.
While we're switching the slides, I just wanted to mention to some folks who are standing up here, there are actually 3 conference rooms we can take you to around the corner where you'll be able to be relaxed and comfortable and see the feed if you're interested instead of standing for the rest of the presentation. So we had made the provisions to provide that for you. So follow me if you want to go to a conference room and relax.
Okay, thank you, Fred. So, Scientific Atlanta, indeed, that is where I came from. And so I normally introduce myself as saying I am from the south, but the south of England. Slight difference between the two. So, first of all, it's just great to see so many people here. At Cisco, we're really happy to be hosting the event, having the opportunity. And it's just great to see such an attendance, and glad that the snow came when it did. What I wanted to talk about is, ties in just totally from what Fred laid out right at the beginning there, which is, and we view it as kind of, we use the term professional media network, and evolution or revolution. One thing that I've learned in 20-something years in the video space is things don't necessarily move so fast. And then, all of a sudden, they move incredibly fast. And then you go back to not moving so fast. So it goes in cycles. And so, whilst it's something where we can see that there is certainly a lot of challenges in terms of moving to an all-IP fabric, there are ones that are being knocked down with each passing day through a lot of contributions, people in this room and outside of this room made. So, let me step through this. So, no surprise, it's yet another IP convergence way. We've seen them time and time again. We saw it with enterprise in the 90s. We saw it with telecoms in the 2000s. I've been seeing it in just general digital video in the last 10 years and perhaps a little bit before that as well. But now specifically in media production. I think it's a real opportunity and an area where, you know, standards are the single most important thing from our perspective, and certainly something that we contribute to drive the interoperability that needs to be out there. The things that we're seeing is obviously in this space a move from centralized to decentralized. Again, things that we've seen wave and wave again. And also this move, as was mentioned, to a converged IP infrastructure. And I'll talk in a little bit some of the challenges that have to be overcome to do that. I'm sure a couple of the other speakers are going to go into it in much more detail as we go through the evening. I'm just the setup guy in that respect this evening. So our approach, the migration is starting. The desire is there, the belief in terms of the savings that can be achieved that Fred was outlining in his presentation are absolutely there. It gives the ability to drive a better differentiation in services. And when you think about it, the IP wave has happened on the delivery side, it's happened in the home, and if we can actually bridge production into both of those as well, it's actually going to open up a lot more opportunities to rapidly get content through the workflow. It's also going to take out a lot of middle steps in the workflow as well, where, you know, today things may go through multitudes of encode and re-encode processes that you may be able to flatten that a lot more. But we need to get it onto a common infrastructure to be able to achieve that. It has to be transparent to the end user. The systems that are in place today, the experience of the people that use those systems to create content, this is not about changing that. It needs to be transparent under the covers and gain the benefits. And as we look at it, you know, a software-defined network approach is part of what we think is important. Our view is about enabling the underlying platform to allow innovation to happen on top of it. Innovation through platforms that allow that interoperability that are driven by the standards. A lot of the standards work that's been mentioned here. 2059 is an example, something that's coming along. So the challenges and the requirements, they go hand in hand. So precision time and sync was mentioned already early on, something where we have to get to microsecond accuracy, and certainly areas that in the IP fabric on the switching and the routing where we have to get the times down there, and that's a lot of work that has been going on across the industry right this second. Driving low latency, driving resilience across these networks. Everyone is used today with the SDI infrastructure of how, you know, bulletproof it is because of the nature of the interconnect. We have to make it the same in the IP space. And security as well. One thing, as soon as you open up, you know, an IP infrastructure, that's the first thing you've got to worry about is what is going to happen to that data on that network. So an area where we can bring collectively a lot of learnings, a lot of capabilities that have been done in the other IP media transformations that have happened and make them applicable into this space as well. How do we get things done? It has to be through relationships. It's all about interoperability. Interoperability comes at the first level with standards. It comes with partners working together to help drive those standards, put them together and see if it works. It's not about just doing paper design in this space, especially if you really want to get to the most efficient solution that you can. I'm sure I'm doing some disservice to some people in the room who work with us and are partners, and I apologize, but doing a lot of work right now with a lot of key people, and I think it's a testament to the interest in this whole transition to IP that so many people are involved in it right now. So as Fred said, existing environment that everyone's very, very familiar with. I won't walk you through this. It'll probably bore you to tears, given that you live with it every day. However, what we are looking at is how we take this across to an IP fabric. You know, one that gives us a shared medium that all of the services can ride across. One where the applications that are riding on it, what we see, you know, with application-centric interfaces, it's the applications that know what they need out of the network. They know the resource requirements they need. They know the timing constraints that they need. These are the things that you need to have exposed from the IP fabric and the way that you orchestrate your services across this. And putting all of that together to drive the appropriate policies so that you can guarantee the service flows and, again, make everything very, very transparent. So we see this migrating to IP on the IP fabric. Media data center, which is something that has been, you know, growing in lots and lots of spaces, as we've been talking about earlier. The use of media data centers is getting embraced very, very quickly right now, and also being used to actually drive things like file delivery between studios, other things like that. But now being able to tie that into the production side as well. So we're flattening again and having the ability of cost savings, getting scale, getting efficiency. And then the control system is there to connect up the fabric and all of the other entities that are sitting there in the system. So as we look forward, Cisco has a very simple view. Yeah, this is not this is about enabling an industry transition. It all starts with where a lot of us in this room start, which is in standards meetings, driving innovation, interoperability, which goes hand in hand with that innovation in standards, because it's only through, as I mentioned, that interoperability, putting things together, plugging them together, seeing what works, seeing what doesn't work, revising the spec, that you're able to drive it forward. And doing that with an open system of vendors. It's not about proprietary solutions. That's the one way this transition will fail, if it is closed proprietary solutions. And then finally, again, another element that Fred brought up at the beginning with off-the-shelf hardware platforms. That's what you need to get this on and then benefit from the scales that we've seen time and time again with Ethernet and IP efficiency. But another way, there should just be a big, no purpose-built appliances in this system. It should be built on generic, off-the-shelf equipment. Leveraging an IP fabric, driving a secure environment that gives us the resiliency, the time, latencies and reduced needs that are needed there to build the best system. So that's what I wanted to say this evening. I think it sets probably the tone for our next two speakers in terms of how to move forward, and you're going to get a lot more detail on a couple of the elements that we've touched on, both Fred and myself here. So looking forward to hear the rest of the evening. And again, from Cisco's perspective, very happy to have you all here, and looking forward to an interesting evening of discussion. Thank you.
Hugo Gaggioni is one of those people that, particularly in this venue, doesn't need a lot of introduction. He's certainly one of the more respected long-term innovators in the industry. Hugo is Chief Technology Officer and Vice President of Technology at Sony Professional Solutions of America, which is a division of the parent Sony Electronics. He joined Sony in 1988. He holds several patents and has authored 40 technical publications in the area of video engineering, digital filter banks, HDTV, UHD-TV devices and systems. He's been involved in a number of activities and holds degrees in telecommunications, systems engineering, electronics engineering from the University of Essex in Colchester, University of Pennsylvania, and Columbia University, respectively. When I first started searching about Hugo, one of the things I ran across, in fact, I think Mike mentioned it on a call we had with Hugo, a broadcast and cable write-up. And I didn't realize that Hugo worked with Larry Thorpe. And we had a chance to chat tonight. Larry and I started to work at RCA in 1965. Larry came in January, and I had come in the previous September. I was in the systems engineering group. Larry was in the camera design group. And I just didn't know until I read this that Hugo, and I was tempted just to throw away the Sony official bio and use the broadcast thing, because there's a great quote at the end of this. This broadcast article, they interviewed Larry, and he had several good things to say. He says of Hugo, he has a great gift, Thorpe says. He's very skilled at presenting and explaining difficult technical things. If we were in front of a group of managerial people, he could dumb it down. If he were in front of technical people, he could more than hold his own in front of top experts. So Hugo, it's time to dumb it down for us.
Okay, good evening. Thank you very much for this opportunity. And I find myself in this paradox that I have to make a presentation under 30 minutes, and it's very rare when I can achieve that. But I'll give it a shot. I have a lot of slides, and I'll PowerPoint you to death. All right, as it has been said already, that our goal, our vision is to move as quickly as possible from an SDI-based infrastructure that we have enjoyed for many years, in the early 90s, to a complete IP-like production system where we don't sacrifice any of the benefits that we have learned through our experiences the last 30 years. And also, not only the handling of video and audio information, but as well as control signals and co-sharing the bandwidth with file-based systems. This is not only for operations in a centralized or localized environment, such as in a central broadcast station, but ideally it's to interconnect locations, and especially, as you will see later, it's a great advantage to try to benefit for the bandwidth that we have in the large telecommunication networks to interconnect regional stations as well as sport arenas, to relocate resources from the stadiums and control them remotely from the broadcast station. These are some of the benefits that some of them have been mentioned already, but the use of a commercial off-the-shelf product is very, very important. It is true that there are solutions that already exist that are proprietary and they are extremely efficient. But ultimately, we would like to ride the way for the improvements in the IT technologies, and the use of inexpensive or commodity switching fabric is very important. The reduction of total cost is extremely important for broadcasters, as we all know. Also, flexibility and agility in changing formats. You know, we converted to HD just a few years ago, but now we're moving into 4K and probably in the future to 8K. Therefore, ideally, we would like to build infrastructures that do not change as quickly as the video formats are changing. Also, ubiquitous accessibility is very important, and this is tied to the distribution of broadcasting and production facilities, not centralized in a single place. And also the capability of gathering data, analytics of the system, something that is not possible with SDI infrastructure. We are all for standardizations. We have worked very, very hard during the last 8 years inside SMPTE to try to create standards for the generation of protocols for IP intercommunication. Fortunately, not very productively, but we have given a shot. And now that we have other committees, we have the EBU, the Video Services Forum, and all of these folks are trying very rapidly trying to put some sanity on the different ways to achieve video and audio information over IP. We developed a solution about 4 years ago. It's a point-to-point system that we use very successfully in a commercial way. And that was our first generation of IP, video over IP transmission, but it was a point-to-point, a very dedicated application. Our goal is to achieve complete multi-point to multi-point interoperability. And we have developed a number of specific LSI devices that I'll talk about later. And we are currently now talking to a number of third-party manufacturers to establish a development cooperation. Look at one of the problems that we face today is that internally in a broadcast station, we may have a main router and all of the different facilities inside the broadcast station that are all interconnected with HDFDI. But if we have to tie to other locations away from the main station, we use tie line management, which entails of doing electrical to optical conversion, going over fiber and then doing the opposite to the other end. It would be very nice if we could just simply have a single infrastructure of a gigabit, 10 gigabit, 40 gigabit cabling devices, infrastructure, so that one single fabric encompasses all of the different venues of the facility. And this involves switching at the layer 2 and layer 3 with full redundancy. Another major emphasis on moving to IP is something which commercially is very important to us right now. The major outside broadcasting trucks are for the most part, dedicated to the major sports events, the World Cup, the Super Bowl, the major tennis operations. But it's almost impossible to dedicate sophisticated OB trucks with all of their sophisticated equipment to college sports and localized sport applications. Then the voice of customers, a lot of customers have told us if there was a way to enable remote production so we can send minimum amount of equipment to the local arenas and then try to achieve real-time operations of those cameras and those recording devices away from the arena and relocating all of the resources in the main broadcast center. That would be a very, very important business solution to enhance the availability of new applications in sports. We have created something which we call IP Live. It's a live production environment, and we are talking to a lot of manufacturers. We have dedicated development efforts with some of them. And our goal is to have multiple solution expandability. Our number one goal right now is HD and 4K. We need to establish high reliability, and I'll talk about that later. And as much as possible, although we work with proprietary solutions as well, but try to use commodity switching fabrics. Now, one question somebody asked me the other day, why you talk about IP now? If we have been doing IP for quite a while. We've been doing monitoring, controlling, file transfer. But what we have not done is live production, so real-time operations with ultra-low latency, with gen locking over IP infrastructure, and with video stream switching with the same robustness that we have enjoyed with the SDI. Also, probably at this time, we are now looking at new standards or proposed standards that appear to give us some hope to achieve this final goal of doing real-time IP communication. And one of them is this famous precision time protocol, the IEEE 1588, which achieves sub-microsecond accuracy for the distribution of time information. This is going to be the next time code for gen locking. Processing and switching, video switching. This picture gives you graphically more or less what I just said. The audio and video information is extracted, encapsulated. It could be baseband or could be compressed, but the key element is time, the time of the information of that source. Then the PTP master makes sure that those time stamps and transferred over the network and perfectly reconstructed at the other end. Then there is no high-level information. We just simply reconstruct the audio-video signal based on the time and the reconstructed video and audio signal. And this is, to a large extent, described in the SMPTE-NY standard. Now, one of the key elements of the production system is the SDI router. And today, this is the key of the center of our operations. And there are different planes. I have identified 3 planes in a conventional SDI router. The media plane, which happens to be audio and video information. The timing, which today we use a time code generator or signal generator. And we have control surfaces so that we can switch the router. Then the idea would be, can we alter this SDI image, SDI router image, and try to see if we can replace it with an IP fabric that will do exactly the same functions. Let's give it a shot. All right, you have an IP switch fabric, and the media plane It has to be either uncompressed packetized IP information or compressed, depending on the bandwidth of the input signal. The timing is going to be given by a PTP grandmaster, and the control surface could be the same surfaces that we have today in broadcasting, but we need to build gateways to control the IP fabric. Therefore, there is a possibility that we could achieve a complete IP-based audio-video router that will coexist with non-real-time information if we play some tricks here. This is a simple snapshot of what probably is required, but there are a lot of technical requirements. Some of them are now attacked or approached by standardization, but others have not been resolved yet. We need SDI to IP conversion, we need network synchronization, we need a network system manager, which is an overall surface of control that will have control on the bandwidth reservation of the switch. And as you can see, there are synchronous areas as well as packet areas in the environment. Not everything is totally synchronous. General requirements, we cannot remove anything that we today use for a living. Everything that we expect to have in an SDI router has to be perfectly replicated as we transition to IP. Also, as much as possible, try to use generic Ethernet switches. This is probably the great motivation to move to IP. We need to have sub-microsecond accuracy in switching in order to produce clean video switching of these streams. And also, it has to be frame accurate. We cannot just switch in the middle of a frame, as you'll see in a minute. It has to be intelligent. The switching fabric has to be aware of the boundaries of video in order to do clean switching. Also, at least this is a company position, is to have essence-independent mapping. We would like to have different data graphs for audio, video, data. Supposed to have everything multiplexed in a single conduit. And as we also need forward error correction. Correction mechanism because the usual UDP/IP protocols are not reliable enough. All right, and let me talk about some of these technologies in more detail. You may ask, well, do we really need to go to IP? If I'm staying in the HD world and I have amortized all my investments in SDI routing and cabling, probably I don't have to. I'm very happy. The problem is when we move, we transition to a world of 4K production. And as you probably know, a 4K 60p 422 10-bit is going to cost you 12 gigabits per second for 4 3 gigabit HDSDI cable. And that is a nightmare. We cannot have that explosive increase in cabling in OV trucks. Therefore, it's almost mandatory that we move to use gigabit, 10 gigabit, 40 gigabit switching fabric using ruggedized versions of the existing connectors that we have today in the IT world. We have this experience because we have built a number of trucks for 4K production. We used one at the Confederation Cup in Brazil. We did the World Cup, extensive use of very large trucks using complete 4K systems, servers, switches, and it's very painful. As you can see there, the amount of cabling and weight is enormous. And this is not a gigantic truck, this is a camera truck. Then we have done a lot of simulations. We have built a few IP trucks in Japan. And if we were to replace a large truck such as this using IP, we have calculated that probably approximately we can reduce 85% of the weight in terms of cabling compared to a traditional HDSDI fabric. We have developed a device that is a very large LSI that allows us to use multiple HDSDIs, multiple 3 gigabit SDIs, and 4K. And this device has a number of Ethernet outputs, both to support 10 gigabit as well gigabit, and all of the functions of synchronization, PTP, synchronization, and codecs. We have a very special codec, I'll talk about it in a second, which allows us to have very ultra low latency and able to put a 4K signal on 10 gigabit. All right, this is what this chip is capable of. We can put 4 HD signals, conventional HD signals over gigabit Ethernet. We can do 2 1080-60p signals over gigabit, and we can achieve 2 4K 60p signals over 10 gigabit, or 2 4K RAW signals for cinematography connections. The system, as we have it, as we have been shown in a number of venues, we will introduce also at NAB, comprises a stream management that will control the routing and the cross point matrices of the fabric, resource management, do the bandwidth reservation, and assess the capabilities of the different devices to accept the streams. Now, one notion that we have to develop, and all manufacturers are also confronting the same thing, is that we have to be able to identify the streams. We don't have the metadata and the vertical blanking to tell us what the video is. We have to be able to identify the streams. This network system manager, one of the key functions is to do bandwidth reservation, because when we ideally select switching fabrics that are commodity fabrics, they don't have intelligence to know exactly what type of streams you are feeding into it. Therefore, we need to have different lanes in the highway with different levels of priority, control priority, audio video section priority, and on a best effort capability, we will send information that doesn't require real-time communication. We name it audio video network node. Essentially is extracting information from the audio and video signal and place it in the header of the IP packet so that we can identify the different packets belonging to every different streams. Then, using this nomenclature, it's very simple, very easy to simulate a switching fabric similar to an SDI matrix. Therefore, the control surfaces that today we use in SDI can be superimposed over a standard IP fabric. Now, getting into a little bit more detail here is the problem of clean video switching. The most preferred method for switching streams, or a start or stop streams packet, is something called IGMP, Internet Group Management Protocol, and it's a multicast protocol. The problem with this way of doing things is that the Ethernet switches do not know where is the video frame boundary. A frame can have thousands of packets, and if I throw the switch, I may end up right in the middle of the frame. Therefore, there has to be a way to identify the beginning of a frame to achieve the actual switching of leaving or joining different streams. Then we develop a system, and it's made up of 4 parts, and I'll show you in detail now. There is a stream sender, a chip, and a camera, or a switcher, and a production switcher. And those stream senders will be receiving the audio and video signals. And we will extract the information of the signal, and we will convert those signals into IP. Up to that point, everything is synchronized. Then the sender, the chip, outputs all these packets with identifications of the frames of that video. And then now we are in the packet zone. When we do a switching, the switching is executed by the receiving device, not by the transmitting device. Therefore, the network management executes when you punch your signal and you switch. I want to connect this camera to this switcher. You're actually sending a message to a stream receiver, which will be issuing IGMP signals to join and leave streams. Okay? And remember, these packets are totally identified with the network nodes. But there's an overlap period, because the fabric, the switching fabric, cannot switch instantly. Then the device that we have developed allows us to monitor the overlapping of the packets, and there are unnecessary packets before and after the switching point, which happens to be a frame. Therefore, this device will be able to discard the previous and post packets that are not needed, and produce a synchronous, clean switch signal belonging to it. If you want, for example. Then all of these operations take exactly less than a frame of delay. Our codec that we have is under 10 milliseconds of encoding or decoding. Therefore, all delays due to synchronization, switching, response to the switch, because there are different classes of switches, some more sophisticated than others, and the actual encoding and decoding of the signal will take less than 1 frame. Therefore, the output signal is exactly delayed 1 frame with respect to the incoming video frames. And it's totally scalable. From standard SD all the way up to now, we're doing 4K. Okay, in summary, the devices, whether it's a camera, a server, a switcher, will send the identified packets. The system manager will execute the command that a human being is exerting on the panel. The stream receiver, be it a monitor, be it another server, will issue the command for switching. These are the IGMP messages. And the fabric will do whatever thing it needs to do. And the receiving stream will discard the overlapping packets. Therefore, there is a way, and it has been shown now for a number of years, to replicate perfectly an audio-video router using these techniques, these technologies. The other important element is network redundancy. If you know very well, one of the key aspects of SEI is its redundancy. I heard a quote from one of the major broadcast TV networks in the world, TV Global. They said that they've been on air for 50 years with less than 2 hours of the air. That is a 99.99999% of perfect availability. We don't achieve that with IT technology. Therefore, we need to have a redundancy built into our system. The current way certain manufacturers use that is to have a failover fabrics. Therefore, we have a main switch, and if it fails, there is a monitoring surface that switches the stream to the other backup switch and continues transmission. But that is not good because data is interrupted and you can see the interruption in the video. Then what this chip does is that we actually output simultaneously 2 streams. One of them can be connected to a redundant network if you want. If not, you simply have one network. But if you happen to have dual networks, the network manager will detect that one of the packets has been lost in the main path, in the main switching fabric, and immediately will message the receiving device to switch and select the packet that's coming through the other path. Therefore, it's totally transparent. Actually, we have to record the failure to inform the user that something happened, because otherwise you annoy him. Then we have been examining standards. The people are talking about the 2022. And I remind you that 2022 was originally designed to operate on a point-to-point communication. It was never designed for live production. And there are a number of subparts or substandards. And I want to emphasize 3 areas. One is the 2022-6, the 2022-5, I forgot to put it there, and the 2022-7, which is the hit list. And the other standard that we're following precisely is 2059-2. Both parts of the 2059 standard. Now, this is our view. Some other manufacturers agree with us, but currently 2022-6 maps the whole SDI payload. video, audio, information metadata onto a single datagram, onto a single payload, which in our mind is very painful, because if you have to do audio and video manipulation separately, you have to demultiplex and remultiplex the modified audio stream. Therefore, we are proposing an essence independent mapping where the video, audio, metadata payloads have different datagrams altogether. And you simply look for the identification of the stream and go modify that specific payload. The other problem is related to 2022-5, which is the part of the standard that defines the forward error correction block. Because that standard was defined to be a transmission-only standard without switching, the forward error correcting covers multiple packets without consideration of beginning or end of a frame. Therefore, very likely, and most of the time it happens, the FEC covers packets that cross frames. Therefore, you cannot switch. You cannot use the forward error correction. One possibility is just don't pay attention to the forward error correction. But we are proposing, along with other manufacturers, to use FEC, which is block terminated as soon as it detects the beginning of the next frame. Then it's a frame boundary aware FEC. And then you can have your protection of error correction as well as the capability of switching. Now, we insist in having sub microsecond accuracy and the gen locking capability of PTP, and we are driving to try to get as much as possible inexpensive switches. There have been other proposals that use specialized time-aware network devices, transparent clock switches, which are very expensive hardware for switching fabric. And this is the case of ABB. ABB is another standard that is out in the market that requires time-aware devices and only uses layer 2 switches. It cannot work with layer 3 switches. Therefore, this is something that we will not touch. We have no intention to adapt this technology, but it works perfect. It's very strong, very robust, as long as you maintain a layer 2 environment. But if you need to have mixing of multiple sensors across a building using a layer 3 interface, it doesn't work. All right, this is sort of the overview of what we've done. And we are now very rapidly productizing this. We have done some demos at NAB, at IDC was our last demo. We had a very successful production environment between Amsterdam and Luxembourg using 10 gigabit fabrics, and latency was minimum. People felt very comfortable in doing this live demonstration. The products that we are launching are system management, which set up the matrix configuration, cross-point switching, and allows us to interface and interoperate very well with all the manufacturers. Specifically, we have a good development exercise with Evertz at this moment, and all the manufacturers. We are bringing to the market SDI to IP converter boards, and vice versa. Let me just move. This board allows us to have either 4K HDs or single 4K devices. Also, audio multiplexing, up to 8 channels of audio can be incorporated in either HD or 4K. And we're also working, we're not finished yet, on AES-67. We plan to adopt AES-67 in a specialized card to support that standard. We have very fruitful conversation with all of these manufacturers, and we are constantly meeting other manufacturers. All right, just to conclude, the approach is as much as possible try to use generic Ethernet switches, as much as possible try to convince the standardization groups to hurry up because the train is leaving. We can just continue waiting. We are making some proposals to the existing standards to add essence independent mapping, frame boundary FECs. And we hope that this transition will be a very rich one because the IT industry continues to evolve. Thank you very much.
Thank you, Hugo. I certainly feel less dumb now. I don't know about the rest of you guys. Hugo can explain it, that's for sure. I was really glad he went into this area with respect to the difference between layer 2, layer 3, and the difference between Ethernet and IP. Both have a place, but today a lot of people who talk about this stuff and try to work with it don't really understand it. And this was a very good dumbed down version for me. Okay, our next speaker is John Mailhot. John is with Imagine Communications. I first met John, I think it was probably around 2000. We were in video services forum activities at that point. We had an activity that was labeled inter-facility links, and it was all oriented toward, mostly over ATM over Sonnet at the time, and then branched into the IP. And today, now we have 2022-6 and 7 and 5 and so forth.
What it did and why didn't it do what I expected it to do, particularly when you start engineering paths and failovers and things like that. And you wind up banging your head and saying, how do I make the switches do what I thought they should have done? Now, when Google and Facebook and all these companies you read about started building these very large data centers, they had huge problems because they really were trying to engineer for 5 nines or 6 nines of performance and achieve it and have paying customers that expected it. And so they added a whole new layer of complexity and said, well, if I have a virtual machine running my melt server or something and I have to move it to another blade because I know that that blade just failed or is about to fail, sometimes you can tell it's about to fail, how do I get all the network connections to follow it when it moved from that blade server to that blade server? Can I write a script somewhere that, if you're a user and you go to Whois and you buy a web page and you buy some hosting and you pay $37, click, click, click. As a result of those clicks, a bunch of scripts ran that turned up a virtual machine, put a bunch of hosting software on there, and in the time it took them to clear your credit card transaction, they turned up all these services. And their cost of doing it had to be less than the $37 you paid. So they had to do something that didn't involve any people doing any work. And that's hard, right? So where did SDN come from? Because it didn't come from those people. SDN came from researchers at Berkeley and Stanford who wanted to do some networking research. And they had a bunch of switches, and they said, wow, there's great hardware inside these switches, but they didn't want to use any of the software. They wanted to write their own. So they asked Cisco and other people, hey, can you give us all the source code for the switch so we can rewrite it and do our own thing? And I don't think it was a long conversation. But, it at least was productive in the sense that it got to its point quickly. What they really wanted was to turn off the intelligence and have their own software do something to push things into the switch chips. And this grew into a white paper they wrote called the OpenFlow White Papers years ago now, and it was co-authored by a lot of people. And they also had taken a page from other industries, made an industry consortium and a group to try and develop and maintain this idea. Now, what really, hang on, if your mouse doesn't stay in the focus, click, there we go. So what did it propose? Well, it proposed that you could take a switch, you could turn the ports, have some normal ports, and you could have some open flow ports, and you could use a secure channel, SSH, to connect to the switch and send some commands to it. and essentially make a smart management system that was separate from the switch hardware, so that the switch hardware would process the packets at line rate, and you and your software could decide why certain packets were going certain places. And these flow table entries are, you know, if a packet comes in this port and it looks like that, then maybe tweak it a little and send it out these other ports. And the look-like criteria are all the things the switch hardware matches on anyway, the source and destination MAC addresses and the VLANs and the ether types, and sometimes the source and destination IP addresses and protocols and so forth. Now, these entries, they seem simple. They're very powerful, actually. Everything you can do in classical IP essentially can be built with those kinds of flow table entries. You can do VLAN pegboarding, you can do IGMP snooping, you could do a lot of things with OpenFlow in theory. Well, what happened next? Well, the researchers were happy, they went on, they did their research, they graduated. That's their goal, right? Their students graduated. They got some new students. Those students did their work and graduated too. Well, the switching industry business dynamics, of course, are very complicated and got more complicated because the ability to do all this fancy protocol processing is actually the differentiating feature between the really inexpensive switches and the very expensive high, application-specific routers. They aren't differentiated by the quality of the solder joints so much, although there's some delta there too. But they are very differentiated by what the software does. And so this whole bunch of what are called white box switch vendors started to emerge that have no software. They have some open source kernel running, and they speak some version of OpenFlow, and in theory, you could use those switches to do your bidding if you want to write enough code. And so the switch makers are in this conundrum of how thoroughly do you support OpenFlow. And of course, OpenFlow itself became a moving target because there's 1.0, 1.2, there was a 1.1 that never caught on. 1.3 is talked about a lot. There's things beyond it. There's a 2.0 in the works somewhere. But if you really try to find the switch you want to use that has the number of ports that you want and is from a vendor that you think will be around 3 weeks from now, and it supports OpenFlow 1.3, that's a really hard pretzel. Okay, fine. The data center industry, meanwhile, they use the technique of SDN, not necessarily the specifics of OpenFlow, but the technique of SDN to provide all these virtual hosting services and things that you use every day that you don't even know you're using. And all these large data enterprises use it every day. Well, OpenFlow is one little piece of SDN. It's one of these like links in the bottom. Fundamentally, the concept is that the network configuration is driven by some application up in the top that has the term business application. It's the application that really understands what are you trying to do. Then there's this SDN control layer in the middle that has visibility to all the switches, understands the paths, understands the redundancy model, and tries to implement your business need in the network that exists. And of course, then you can have multiple switches and geodiversity, but some common control structure. Now, assuming you're not writing it, where do you get an SDN controller from? Well, there's many, many open source projects. Gee, that makes me feel great. Who writes these open source projects? People who, by and large, either don't have a day job or their employer is paying them to do it, which is, sometimes happens, I guess. There's Beacon and Floodlight and Pox and Iris and Mull. This list is from a couple months ago. There's probably 3 more by now. There's loads of them that came and went, and some of them that are just barely on life support. Now, the website can last a lot longer than the actual support of an open source project. Now, in the meantime, each of the major switch vendors has developed something that is SDN-like functionality packaged as a commercial offering. Cisco has a nice one. Arista has one. Brocade has one. Juniper, I'm sure, has one. Other people have one. They are quite differentiated if you start asking those vendors about what their particular SDN-like thing does or doesn't do. And, some great product offerings out there. And then there is this one thing called Open Daylight that's a funded multi-vendor collaboration producing an open source result. Now, it's an interesting idea. It's an exercise in commercial economics across a lot of companies. Open Daylight, they just released their 2.0 called Helium. They've got 90 more elements to get through, I guess. The first one was called Hydrogen. So this really is an attempt to target all of the different things that happen in the network. So everything from, they have APIs at the top, and then they kind of translate that into service abstraction layers, and ultimately down into OpenFlow enabled switches. They have a little passing reference here to netconf, which is actually a pretty good protocol for talking to switches you actually can buy and would want to use. Other protocols as well for talking to switches. There's a million other protocols there. And they also deal with Open vSwitch, all kinds of other things. And this is an example of a SDN environment that is brewing in the public domain. And it's not bad. It does a lot of nice things. Now, not to be outdone, there's another thing called OpenStack, because networking is one part of a much bigger business challenge for the data center guys, which is really they're trying to operate a multi-tenant hosting data center. And honestly, in some of the broadcast entities that I deal with, they also have a data center that has multiple tenants after a fashion. They might be production and sports and post and edit, and but they compete for resources. They need to be firewalled from each other. There's minus mine and yours is yours issues. They're not so different than competing commercial tenants. And so the data center industry, led by Rackspace.com, but other people funded it as well, funded this big project called OpenStack. And there's a bunch of pieces of OpenStack and interrelated projects, and all this is happening. And so OpenStack tackles computing, and what does virtual computing mean, virtualized networking, and of course virtualized storage, because you can't have one without the other two. And then, oh yeah, your applications live up there. Now with OpenStack, what could you do? Because you can download it and run it. It's all yours. Enjoy. Good luck. Learn something. It's fun. You could stand up your own private cloud, take those servers from 2 years ago, crank them up in your basement, buy better hosting at your house, and run a data center. Your electric bill will be significant, but maybe there's money in that. People do this as a living, not at small scale. You can run applications in one of the public clouds, AWS or Azure or so forth. They all have integrations with OpenStack in some way, and OpenStack provides a nice API for doing that. You can manage and monitor those hosted applications through a dashboard. That's one of the benefits of these systems, is they give you a way to understand the applications that you parked out in the data center. Now, how's any of this apply to SMPTE and video in general? I mean, somehow this all has to tie together, or I'm just talking about an IT thing. Well, we in the television equipment industry, who serve the television production and distribution industry, like to think that this industry is really big and that there's a ton of infrastructure here, and by God, we're all important because we're from the network, damn it, we're here to take names. No. But really, the television industry, the sad truth is not the largest industry. And so for years, we've borrowed and stolen and begged technology from the telecom industry. All those nice fiber transceivers we use for video, they're tweaked up Sonnet transceivers, folks. Be honest, right? And so the telecom equipment industry, you want to talk about people with egos. My God, we're from AT&T and we're here to take names. I started my career in AT&T, let me tell you. It was something back then. It's not such a big industry either. Bigger than us, but not such a big industry. Then there's the big red one. Sorry, I should have made it Cisco blue, but the big red one. And the IT economic ecosystem that includes a lot of things is really big, and it's big enough. I'm from Florida, and in Florida we have these forest fires every October. Set your watch. And one of the things that happens when the fire gets big enough, it creates its own weather. And you can actually see it on the radar that all the other weather clears around it, and this thing creates its own little high-pressure system and makes it not rain where the fire is. The IT industry is frankly big enough that they create their own economy of components and assembly houses and so forth. And it's a self-supporting ecosystem of economics that is just a different zone. So if you talk about why can Moore's Law help and why can Moore's Law exist, it's because of the size of the industry is able to fund the innovation. The largest fab in the world is Intel. What's the second largest? Right, who makes the same kind of stuff, the chipsets that go around all the Intel stuff, among other things. So it's an amazing commercial ecosystem. I don't even know if that's true, but it's somebody, right? Yeah. So, so here we are in television. What does this mean to us? Well, back when I started my career and, HDTV science was just in the process of being invented. I also started in 1988. We were just transitioning in the IT side of the world from shared coax Ethernet, we all used to use coax, remember, to they had this whopping 10 megabit point-to-point Ethernet, which enabled Ethernet to go from a shared medium to a switched infrastructure. And that was huge. And so, we had analog, they had that. We proceeded to have 270 megabit digital when they still had, 10 base T. So we thought, we're 27 times as good. And then we had 1.5 gig and 3 gig SDI, and, that's fine, right? That was quite progressive stuff, hard to do, did it well. In the meantime, the IT industry did not sleep. Their economics created this sequence of bigger and bigger and bigger pipes. 100 gigabit Ethernet is not a science project, it's an orderable item. You can get it from any of the real switch vendors, and you can plug it together, and it's pretty likely to work. So in the meantime, we're working on 12 gig SDI. Cool. Neat. Now at the same time, the 400 gigabit working group is actually charging along, and they, I was trying to get a status update. They're a little murky online because they're working through. The physical layer is a little challenging, but there's enough M dollars behind it that it will happen. Can you peg it within 6 months? I don't know. It might be a year. I don't know. I don't know is there anyone from Cisco that wants to hazard a guess on when 400 gig will start shipping? I think it'll still be during my career. Okay, so there you go. The stuff's real, and it's driven by an economy that none of us have to help. If we all converted to IP tomorrow, it would not increase the size of the red circle by a noticeable amount. So just, for good or ill. Now, what's that mean in practice? Well, it means if I have a Yamaha audio console and I want to buy an HDSDI interface board for it, it costs me like $5,000. And if I have a PC and I want to put an SDI interface in it, that costs, it's really more like $500 now. When I first made the chart, it was $1,000 roughly. And, we don't make that card. Or I can buy a NIC from Intel for, at the time I made the chart, it was $434. I checked yesterday, you can get a Intel X520 DA1, the version of that with one 10 gig cage on it, for $158 on Tiger Direct. How many would you like? That's the onesie quantity for a nobody customer. The cable costs more than that. I mean, so. Now, will IP replace coaxial cable? Well, historically, we and some of our competitors make these big boxes that ship bits around, and you get, 256 square router, it's 15 RU. It's not the cheapest thing we make. In the meantime, from virtually every real switch vendor, you can get a 1 RU box with something equivalent to 64 10 gig ports on it. Usually they're broken into 48 10s and a couple of 40s. There's a couple of variations you can buy on that. And those cost a lot less than a 256 square SDI router, even if you buy some software licenses and other things. Just the economics are so different. Now, what's this SDN thing mean in the video context? Because this is where it gets interesting. And I have to wake the mouse up a little, sorry. So what it means in practice is that we have application-specific knowledge. I know that an operator in Edit 3 hit a button and he wants a certain feed. And then we use that application-specific knowledge to make something happen. So very much like Hugo explained, the controller, orchestrator, whatever you want to call it, knows what IP addresses things are sending on. It talks to the receiving devices and says, hey, you want this new feed. You should look for this new feed. And then also the reverse path of statusing, did that really happen? Did you get your feed? And pushing that back upstream, because operationally, you push the button, the color of the button changes saying, yes, I did that. That's a really important operational thing. Not, yes, I understood that you asked for that, but yes, I actually did that. It's a big difference. And so this is really the enabler for using these commercial off-the-shelf data center grade switches. Now, I throw that little phrase in there, data center grade. You do have to be an intelligent customer when you buy these things. You know, there are a variety of products. They all have different kinds of performance. They have, you know, historically there were Ethernet switches, for example, that were oversubscribed inside. They were built on assuming some statistical gain that not everybody could possibly run every port at full rate. But in the data center world, thankfully, somebody else who's already in the big red circle made a class of switches that have enough bandwidth for every bit from every port to go to every other port at the same time. Thank you, Google and Amazon and Facebook, for driving those switches to exist in that class. So we didn't have to ask for it. Now, what features, what kind of thing would you expect us to do? Well, I don't believe that we will go to IP instantaneously and completely all at once, overnight, bang, you're done, thank you. Because, I don't know, I've worked in the television industry for almost my whole career, and there's still people that keep an analog deck sitting in the bottom of the rack just in case that tape comes in. I've never met a television engineer that would voluntarily sunset a piece of equipment that had even the hope of being repaired. I mean, forget that it actually had to work. Just even the hope it could be made to work in the future is enough to keep something sitting there. Pretty much when the garbage police come through the plant and throw it away despite them, that's the only time stuff leaves. Sometimes not even then. They track it out in the dumpster. So there will be a world that is a hybrid of SDI and IC. It's in many plants. Some have the luxury of a forklift upgrade. God bless you, that's fantastic. Other people have to work in the reality zone. So you have to make the stuff under the orchestrator look like a router to the stuff above it. And that means tallies, takes, statuses, multi-viewers, automation systems, all the legacy protocols. If there's like 10 different router control protocols you have to speak to actually talk to the things above you. That's okay. We do this today. This is standard witchcraft in the television industry. We know how to do this stuff. Now, there's a whole parallel transformation going on that I'm going to mention very briefly about software-defined workflows. You know, this so far we're talking about plumbing. And plumbing is interesting, but you know, it just fits on wires. Different wires, okay, but it's fundamentally, that's a plumbing issue. There's a whole other transformation going on, which is that as the CPU side of Moore's Law cranks along, doing that doubling every 18 months of horsepower that you can buy for the same number of dollars, we've gone from, you know, well, the computer's neat and I can read my email on it, to a thing with a pair of hex-core Intel processors in it right now. Can do, you know, 4 channels of HD ingest, 4 channels of HD playout in a variety of file formats, while tap dancing on the right and adding some graphics and making an output image. No problem, right? We do this. If you pop the top on any of our video servers or editors or other things, they're all just computers inside running software. That whole transformation has happened. The only things left in the plant that are hardware-based, if you will, on the, you know, things that do things inside, are things where the economics just isn't quite there yet. But if you throw in a factor or two every 18 months, you can kind of plot the curve and say, okay, well, the next generation of encoders from the encoder makers, probably going to be all software. When is a, you know, up-down cross converter going to be all software? Well, some of them are already. It's just cost of features, right? And that is the real transformation going on. It's the number of cores, you know, CPU cores per cubic foot per dollar that you can buy is the other transformation that's happening while we're talking about the networking side. And that will actually have a more transformative aspect than moving the signals on IP. Moving the signals to IP is a nice precursor. It's the first thing we got to do, but getting on that cost curve of the software-based appliances and the software-based workflows is what's really going to transform the way we do business and the things we do it with. Now, how do you think it flows? Well, Hugo talked about this, so I'm going to go really quickly through it. There are 3 ways that have been proposed And this is the uncompressed workflow, or the compressed but chopped into segments that look like frames anyway. Similar idea. So there is a scheme called source time that is, you know, Thomas Edwards did a nice demo of this with a different switch maker. And it could be made to work. You could time the plant so all your sources are lined up, and you can do some preset routes based on matching some fields. He did it with ACLs, which is a way in the switch of giving a specific rule that matches some header fields. It requires source timing. I'm tired of source timing. Are you tired of source timing? Mm-hmm. Source timing is really important when you're shooting an event and you have multiple cameras and you don't want to have crazy things happen in transition. But the deeper you get into the plant, you get into playout centers, it's kind of less tied into the universe. Except that we've grown accustomed to the side effects that if all the sources are timed, you can do some switching in your router that is almost clean and not very quiet. Now, so in source timing, you got your feed, you switch to the other one, and because they were mystically lined up, you could do that switch in the switch. There's some scalability challenges in there, and it requires source timing. I don't like this approach, and this company don't like this approach, and I gather some even like it either. Feel free to say different. There was another scheme that got demoed along the way called switch timed, where they actually had an FPGA in the switch, and you could do the same thing, but it had some buffering and a little more complicated alignment logic. And it still requires you to time the switches, which is still a pain in the neck, or somewhere else. And it requires a very special switch with a very special FPGA and a one-off version of software, and it's the complete opposite of commercial off-the-shelf. Remember that whole commercial off-the-shelf thing that was the virtue of this? No, let's not do that way. So we advocate, and Sony advocates, and other people advocate as well, this concept of destination time switching. And you might call it different things, but the idea here is, if you're a destination and you're receiving a stream, great, you should do that. And when it's time to switch to another, something tells you to switch to that other feed, and you do. You start getting the new feed, you synchronize them, you switch to the new one, you drop the old one, you go on your way. We've been showing this around for a year in places. Some of you have seen it, others give me a call later, I'll bring it to your office next Thursday or something. I'm busy that. But it is kind of a standard witchcraft. And by the way, that switch at the receive side can be as simple or as complicated as you want to make it. Ours, we made it a fully frame synced clean quiet switch. Why? Because we had FPGA code around for that, because we do that. It's actually better than an SDI switch because it's actually clean and actually quiet because we did a little audio duck on it. And it's fully redundant. Because although I draw this as one switch for simplicity, the whole notion of this SMPTE-2022-7 architecture is these switches, they aren't very expensive. Use two, main and protect, except they're really main and main. Every packet is in both switches. The receiver gets them all. The receiver matches them up by sequence number. It just works. It works fantastically. And it's interoperable among a lot of vendors. There's actually a big interop event going on in Houston right now that all these vendors are plugging together. So if you come to VidTrans in a couple of weeks, you'll see the output of that. Just a little plug. Somebody has to tell Richard I gave a plug for it. So that's kind of how the destination time switching works. So how do you build a plant that's got both? Well, you could have your big SDI router in the core, maybe you already have one, and you throw a few translators in there or next to it or near it that convert things to and from IP. And that's a great way to start. It's got a really tough end game. Because in the end game, you wind up with a whole lot of translators and it's still a video switch in the middle. But, you know, if it's where you are today, it's a fine approach. You could go whole hog the other direction and say, I'm just going to go to IP and the things that are SDI, I'll translate them. And that's great if you have a lot of things that are natively IP. And, you know, the more IP things you have, the better the economics of that approach are. Then the third approach is to do a sort of a hybrid core. So you have hook your SDI things to an SDI router. You probably even already have that router sitting there. And you hook your IP things to IP switches, and you do enough translation between them to do what you had to do. And this, anybody here lived through the transition from SD to HD? This picture looks real familiar. If you just change the words a little bit and kind of squint and don't remember, it worked. It got us to where we are today, you know. We're still in our chairs.
Transition from analog to digital.
So I'm told, yes. So, you know, now there's an interesting thing happens once you have enough IP-based signals. That is that you can kind of reorganize the physical architecture of the room. You can say, well, instead of having that cable tray that has to, in the middle of the plant, hold every cable and those, you know, screwed into the concrete and everything else, maybe I'll put the A switch over in one end of the room, the B switch over in the other end of the room, and I'm running these fibers that are just a lot smaller. And it becomes a much more interesting distributed plant because these OM3 fibers at 10 gig, you know, they get you 300 meters, which is about like coax on a good day. And the single mode fibers get you like kilometers. And the single mode SFPs, if you buy more than one of them, are not that expensive. And if you're building a television plant, you're going to buy more than one of those. So you can do some very interesting architectural things that relate to the building design and how things flow in the facility. They're very different than coax. And it's an interesting, liberating thing. Just the weight of the cables that, you know, Hugo talked about in the truck, it's true. You know, the math works out for some of this stuff. And you say, well, you know, how many M dollars on my spreadsheet is that? If it's the difference between putting more steel in the floor underneath where finance decided your new machine room is, there's a lot of dollars in that. So, I could be done. No question. Not one?
Interesting stuff.
Need a runner, Josh?
Here and seeing happening now.
I take it.
One of the things I wanted to mention is there was an email that came out to SMPTE membership a couple of days ago about a new online program that's going to start. Registration started already, and I think the first class starts on April 6th or something. Where's West? Yeah, I just want to make sure we get the date right. But you can go to SMPTE website now, and SMPTE Education has they have a couple of new programs they announced the other day. One is on UHD architecture or something like that. The other is on IP, online IP facility techniques and practices and so forth. So with that, I believe there was supposed to be a couple of microphones around.
There are.
There are probably a few questions. I don't know who wants to be first, but if you'll signal for a microphone and we can.
Please speak up. The microphones have been a little spotty.
You go and John joined you up here.
Question for Hugo.
Mention who your question is for, and then.
Question for Hugo. What's the difference between the new protocol that you're coming up with and FIMS?
Completely different. Yeah. It has nothing to do with it.
Okay, why?
Because FIMS has orchestration.
Guys, stand in front of the mic, please, for the folks who are.
The question was, what is the difference or similarity between what we are doing or SMPTE, any of the subparts of 2022 and FIMS? And the question has no relation. FIMS is an orchestration layer. It has nothing to do with.
Aren't you talking about an orchestration layer in some new protocol that you're coming out with?
FIMS establishes APIs between your native software and whatever is the orchestration layer. I can have anybody's control surface going through, if FIMS standardizes an API to control my network manager. Has nothing to do with it.
If you're going to ask a question, please mention your name and who it's for.
Daniel, for Hugo. Hugo, you didn't make it that easy enough for this manager. You didn't double down enough. In the middle, you were talking about switching in production, and you switch from production to switching for and then you lost me. Because you're talking about trucks, production, studios, cameras, and then talking about clean switches. Were you talking about the Cisco switches? Were you talking about the video switcher or the router switcher?
When we talk about clean switching is trying to mimic the experience that we have today with SDI. As John mentioned, it's going to be a transition between today's SDI environment to a future where everything is IP-based. Therefore, I'm going to have SDI coming in. I have to convert my SDI into IP. I'm going to go into a switching fabric. That switching fabric is going to be controlled by a system manager. And that system manager will look to an operator like a router. And you're going to say, I'm going to switch camera A to monitor B. And when you punch that button, it has to behave exactly the same as today's SDI. But it has to go through a switching fabric, which is IP.
I'm just going to comment on some of that. Remind me of, there's a review of this software-defined networking buzzword that says you take the existing so-called data network and separate the data plane, data transport plane from the control plane. Because today this control plane is basically embedded in the network, and you have a situation where the network is essentially hardwired programmed to do certain things based on mostly source and destination addresses and some other protocols to modify things for different purposes. And this idea of orchestrating all of that, in my mind anyway, is more along the lines of, are we managing content asset management from an asset management perspective, or are we managing content that's moving around by manipulating the control plane in a network?
Any questions from that?
Another question or two? How much more time do we have, John?
We have lots of time.
Oh, okay. Maybe we start a fight or something.
Question over here, microphone.
For Hugo. You said that this is probably specific, the encoder box, the encoder and decoder that, take in 4K video, send it out over, a 9-bit fabric, that there's 10 milliseconds of delay on encode and decode. Are the codecs used open at all? Is that proprietary Sony information?
This is we call it low latency video coding, LLVC. We have submitted it to SMPTE for a recommended practice or an RDD. It's proprietary, we built it. It currently exists in all of the studio cameras that happen to use Tri-X. It uses wavelets. And one question that people keep saying, well, you have a proprietary codec. Why don't you use JPEG 2000? But what people don't realize is that JPEG 2000 is defined based on frames. The standard applies to a complete frame. And if you were to use a JPEG 2000 off the shelf without any modification, it will not be low latency. It will not be able to work in production environment. And all manufacturers that use J2K chips have to modify the chip to do line-based coding. Therefore, my encoder and my decoder has to be matched. Another word of proprietary.
Mm-hmm. Did you start from the JPEG 2000 type encoder?
Yes.
Okay.
We modified.
I did a little quick math, and I thought it was about 10 lines in HD.
That would be my
it would have to be. Yeah.
Excellent.
Wow.
Microphone.
Hi, you're on.
Okay,
Bill Handler. For any of the guys, so we're talking a lot about routing and distribution. But Hugo, you guys do production switchers where you're doing transitions between the signals and you're combining the signals together in the the graphics world, you have equipment contributing signals that has separate alpha that tells switchers how to composite it. Are there any general considerations other than relying on Moore's law to give us ever-increasing CPUs for ways that different contribution formats can be handled in that production switching environment in the IP domain?
Listen, we run a business. We don't have fantasy land. We bring IP packets to the switcher. We decompress, and once we are in the signal processing domain, it's 4K, HD, 422, 444, alpha. It's real video signal where we manipulate. We're not going to implement fancy transitions and image manipulation on packets.
Yeah.
No, it's true. I mean, there's a world where there's a lot of different formats, and in a production environment, you hope all the cameras are in the same format. Adding to what Hugo said, in the production world, you tend to have everything in the same format, and you reach the switcher and you do your thing. There are, over time, maybe we'll have network-based effects and things, but if you peel back the onion on those, it's take the packets, decompress the signal, or descramble the signal, or whatever you got to do to get down to buffer full of pixels, do your effect, and then undo it and put it back on the wire. And that's one of the reasons that we're a big advocate of the uncompressed, 2022-6 kind of workflow. If you think about how these things move into software-based workflows, the lowest software footprint is to have pixels on the Ethernet come in, drop into the frame buffers, ready to use, compared to having, say, JPEG 2000 come in over IP. Yes, it has less network bandwidth, but then you chew up 6 cores, 8 cores, decoding it, so you can touch it, add a bug or something, and then spend 8 cores re-encoding it just to save some network bandwidth.
And then wait till it shows up to the rest.
If you look at the cost per port of 10 gig switches, that cost is coming down faster than the cost of most things. So don't try and save bandwidth. Try and save processing.
How do you put 4K into 10 gig?
It compresses.
Thank you.
By the time there's enough UHD out there, then 25 gig Ethernet or 40 gig Ethernet will be at the right point on the cost curve. But in the meantime, then we'll be at 8K. There's places where compression makes sense. I don't disagree with you.
Another question?
Yeah, I'm Colin from NBC, and you mentioned bandwidth reservation and similar to ABB's stream reservation protocol. How does this work when we have multiple protocols, like AS67 and SMPTE video on one network, and perhaps even things like FTP happening, or if you merge with these networks, things like that, that could come up as a topic. Is it all orchestrated by one manager, or what happens if you have multiple managers? Do they have different priorities? Where do you see that being managed?
Okay.
The way we implement it is we have a system manager that controls everything. The way we are interfacing with other manufacturers is that we use their software control surfaces to control our system manager. But our system managers that have full knowledge of the intelligence or lack of the switcher to make sure that we have best effort streams, real-time streams. We do the bandwidth reservation ourselves.
That's talking directly to the switches.
Yes.
Okay. And then, so if there was some other types of media data that's flowing on these switches for other purposes, they would be given some other
priorities.
Exactly. Okay.
Yep. No, I essentially a very similar approach that for the real-time streams, we carefully manage the bandwidth, but we also do flow priority marking and the good old toss bits. And the switches actually do follow those if you set them consistently. And so it's a combination of in the top priority class where you have the real-time flows, you manage those very carefully in the control system. and presumably with reservation and so forth. And that's the benefit of being the control system, is that you know why that feed is going that place and what ports it's going to, what ports it's not going to. You actually can contract. And then for the lower priority traffic, like the FTPs of the files and things, which, by the way, for the playout server, that's not actually a low priority signal. It might be lower than the real-time stream, but it's pretty important that the preload happens. Then those are marked lower, and we do count on the switch to do some, to implement priority classification and priority queuing.
Hey, John, we're not going to lose VLANs, are we, by having these new high-performance switches?
That lose them or use them?
Lose them?
No, we use them.
Okay.
Sorry, the question was, will we lose VLANs? And no, I think VLANs are a core part of keeping sanity and order in a large-scale IP network. And
the only way to keep
priority
priority
tagging can be tied to the VLAN tagging, and that's quite important.
Any other questions?
Yeah, my name's Pete Huffman. Just a quick question. When you're talking about remote sites, like having out at a remote, say, stadium, having the cameras, and then sending everything back to data center or the head end, you are using existing internet networks? You're just, or only a...
Dark fiber dedicated.
Got it. Kind of thought that. But.
Or, a service furnished by a carrier that has a guaranteed quality.
Yeah, I was just going to say, because if you can't keep those pipes open, then you wind up getting... Yeah.
Well, and pretty much any venue that hosts major events in the U.S. has fiber to it from at least 2 carriers. You might not like the cost of renting that fiber, but that's a different question.
It's the only way to really do it.
There's another kind of a point to make here, and it has to do with the fact that most people picture the internet as this one great big IP network out there. But all the carriers have a set of facilities and services that make up the internet as we know it, the so-called best service or best effort service. And then they have other, what I'll call network facilities on the side to make up virtual private networks, the so-called VPNs, and point-to-point private lines or equivalents, if you will. So there's this set of facilities or services that are available that you have to figure out if you want to do what you're talking about, exactly what you need for bandwidth and connections and quality of service and grade of service and a whole long list of things. Maybe one of these days we'll get a couple of carriers in here and have a lot of this kind of conversation with one big area there.
Hi, my name is Luis, and I have a question to the panel about the methods of measuring and troubleshooting those kind of topologies. And the SDI, you hear me?
Just like,
yeah.
Get close to the mic.
Just speak up a little bit.
Speak up. In the SDI world, we all have different instruments to test and measure the quality of those signals. This new topology and architecture that you guys are talking about, we're going to see those kind of tools and measurements evolve, or we're going to use IT troubleshooting techniques that we presently use in networking?
Yes and yes. The question was about test and measurement and how. And will it be IT stuff? Will it be more broadcasty stuff? And I think it's yes and yes. The Ethernet switches do give you some telemetry. It's not as wonderful as you'd hope, but they give you, a lot of statistics about ports. There's a nice protocol called SFlow that's in most of the switches that gives you, what are the top 5 multicast groups on this port. It can't give you the top 6 for reasons that are just unfathomable, but it gives you the top 5. And it does a statistical sampling of the traffic to tell you what's happening. It's got its limits, but it's very handy. And there's tools like that. One of the beautiful things about the big red circle we're talking about is that it does create a lot of tools, some of which are useful to this kind of thing. That said, there will emerge a whole set of test measurement equipment that can, plug into the IP and you type in an IP address or you do something to get a signal to it and it'll put up a vector scope or something like that. I'm sure that someone will make a vector scope with a 10 gig port on the back. I don't think it's the odds, frankly. But somebody will do that. The usual suspects in the test environment generators from Anui and from Packet Storm. You know, there's a whole other set of vendors that are just dying to meet you.
Yeah, just a couple of points on that. If you probably heard the IT people talk about protocol analyzers. This is a pretty rich field. There's at least 2 out there that are free.
Wireshark.
Yeah, Wireshark and maybe Ether Reality used to be, they merged with Wireshark or something. But these are both organizations that do nothing but just kind of like ham radios, right? Where they make protocol analyzers. And there's another level of this that I think I see. I'm not sure, but I'll just put it out there for the moment. Is if you can picture yourself sitting in a facility at some point and you see a problem with a picture or hear something in the sound, and the underlying infrastructure that's supporting that sound is this maze of fibers and wires and other components. You're in a situation where in the old days, quote unquote, or the SDI days, we have a passive network. And in this new world that's coming on, it's all of a sudden not passive anymore. It's active with switches and routers and network interface devices and on and on. And the challenge, whenever there is a problem, is to pinpoint where the problem is quick. And you can imagine as easy as I can that, frankly, as I think it was Craig Kuttner said to me one day, he said, you know, ping and trace route won't cut it. So there are new methodologies, new practices that have to come into play to deal with this new set of infrastructure with improved workflow, or in other words, it's fewer pairs of hands to deal with the day-to-day operation.
Can I comment on that for a second? Because there is some truth to that, right? Many times, you know, if you look at how a lot of traditional facilities work today, you've got a multi-viewer with a whole whack of pips on it, and you've got a set of patch cords and a patch bed. And that's kind of the two things that are one in each hand. And you say, well, if it doesn't look right on the monitor, then I'll just go start patching through. Most of the equipment you buy actually today gives you a lot of telemetry about its happiness level and how many, you know, is the signal really good? And does it have CRC errors? Does it have, you know, just about everything that today touches SDI provides through SMPTE or through some other interface, all kinds of telemetry about what's going on. The vast bulk of that telemetry in most facilities goes nowhere. But that's a choice, right? That choice is enabled by, well, just give me a bunch of pips and I'll have the people watch the pips. And as we move into IP, it's going to be more important to take that telemetry that the system gives you and organize it into displays and, you know, dashboards and other things that provide operational visibility. It's not a lack of tools. The tools to do this exist, but it's a lack of need. The trade-off between the cost of setting up those tools and using them versus the error-event ratio of the chain today didn't justify it. I think in the future it's going to be more important.
More like a 290 display.
Or, well, 290 for transport stream,
Yeah.
the equivalent thing for
Right.
this,
Yeah, there's a couple of standards in this area that you may not be aware of. There's 2 from ITU and 2 from IEEE. And it's divided into 2 parts. One part is for acceptance, or what's called service activation methodology. That one is ITU 1594, I think. That one is free from ITU. And on the service side, there's an ITU standard Y.dot 1731, and there are 2 IEEE standards that are used for monitoring and alarm, or as they call it, I think something like operations administration and maintenance. It's like a telephone company type term. But there are standards for these things out there that enable test and acceptance of a facility when you take delivery from the service provider, And then once it goes into operation, there are other standardized ways to monitor that facility and get alarms and so forth.
Any other questions? We have a question from Jim O'Brien, logged in on the WebEx. His question is for Hugo. He says, Sony equipment and camera ports are great, but will Sony Microelectronics or another part of Sony provide these LSIs to other industry manufacturers to gain scale? If it's decided already to make them available OEM, is there a time frame of availability?
Wow, that's a heck of a question. Yes, they will be available. They will become available, and probably in both the cards, not the chip itself. We are in discussion with another manufacturer.
Hopefully that satisfies you, Jim.
Any other questions from online? Please stand by while we present the plaques.
Just one more thank you for coming out. I think this is one of the highest attended meetings we've had in a long time. I think Tim said earlier, you may not have had this many people come to a meeting. We're glad you're here, and we hope to have more these sessions in the future.
Thank you. I appreciate it. I have one for you as well, Brett.